Okay, here we go. Wampadoo. Okay. Right. Hello. 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 Let's do this. Do this. Okay. There we go. I'm not sure why, but okay. Okay. That's fine. No problem. Hi, everyone. Hello, everybody. Hello, 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 hello. All right. You're back. We're going to go ahead and get started here in a few minutes. We'll wait for people to come in. I came in just a little bit behind here today. So we'll give everybody just a few minutes here and we'll get going after that. I see some people in the chat. All right. Good afternoon, everybody. There we go. Get some people in here. We'll get going. It'll be great. Okay, that's fine. That is fine with me. Okay, hey ho. There we go. Alrighty, what are we doing today? That's a great question. Oh, we're doing that. Okay. That's pretty easy, so that should be too much of a problem. Alright. Yes, yes, yes. This, that, and the other thing. Alright. Alrighty. We'll wait until 4:05, about 3 more minutes, and then we'll go ahead and get started. All right. A few more people come on in. Oh, looks like we got a few people in. All right, all right. Hi, Gerda. How are you? Okay? How's your afternoon? I hope your afternoon's doing rather well. It's been nice and relaxing here today. Pretty easy day. Easy time, easy life. You spent about an hour on Alex, so it could be. Oh, yeah, sorry about that. Hey, how's it going? Hello, hello, hello. Arabian Andy, how are you, my friend? I hope you are doing very well, my friend. All right, we're almost set to go. Seems like all the topics take 3 times longer than the. Oh. That's like if you're looking at a clock and things take much longer when you're staring at the clock rather than just, doing what you gotta do. Maybe it's something like that. It's okay. As long as you're, making progress, that's good. Just progress is all I want. Positive progress. All right. I gotta get going here. All right, let's do it. All right. Okay, let's get started today. Welcome back to Thursday, end of the week time today. So today, as a friendly reminder here, remember that the test is due next week. Okay, so next week here, the test is due. So please be sure to finish it by that due date, which I believe set for like next Monday. So please be sure to finish the Unit 3 test. That's the Chapter 3 test there. Again, that's all set and ready to go for you. All right. All right. So today, we're gonna finally get into the next unit here, the next chapter. All right. And well, actually, if you would believe it, we're actually 8 weeks through the course after today. So we're halfway through the course. Look at that. So I know it's kind of amazing how fast time flies. So in any case, um, let's go ahead and take a look here at what we're going to be doing here today. Today we're going to be looking at two types of other functions. We're going to be looking at exponential functions and logarithmic functions, and they have a lot to kind of do with each other. So we're going to look at sections 4.1 and 4.2. We're going to explore a little bit about each. Okay, so let's look at the first question here, which says, what is the definition of an exponential function? Okay, so let's go ahead and do that out right now. Okay. Go. Okay. Okay, so the definition of an exponential function is going to be y is equal to b to the x power. So something that looks like this. Okay, y equals b to the x power, or again, you can also modify it to f of x equals b to the x, putting it in function notation. Okay, so again, they mean the same thing as we know. F of x is the same thing as y. There's no difference between the two. Now let's talk about what b is here really quickly. So b here is going to equal the base of the exponent. So b is what we call the base of the exponent. Whatever that base is, it could literally be any number. It doesn't really matter, all right? But that is what b is defined as. Okay, so we're going to be looking at different exponents and how to deal with those. Okay, it's not going to be that tough. All right. Um, Otherwise, I guess a couple other things is b is going to be positive. So they're kind of minor notes here, but so b is always positive, and b is now where is it here? I gotta put that there. B is not equal to 1. All right. And I guess one more thing I guess I can throw in here as a side note. And x is any real number. So x, the power can be whatever you want it to be, but b is always positive, so we're going to have at least some positive number, and b is not 1. All right, so that's fine. Okay. The reason why it can't be 1, by the way, is because it'll always be 1. 1 to any power is 1. So, all right. What is an important rule of exponents to remember? Okay. Now, there are several rules of exponents here that are certainly very important. But if there's one rule of exponents that is incredibly important here, that majority-wise has stuff to do with, say, negative exponents. So the one I want to focus on, the property here, because there are various properties here with exponents, but this one here has to do with if you have, say, a to the minus x power. So if you have a to the minus x power, okay, remember that basically, or you could call it b to the minus x power, really, it doesn't really matter. In any case, what you could do is if you have a negative exponent, then what happens is you move it from the numerator, in this case, to the denominator. So you could have 1 over b to the positive x power. Or, that's the first one there. Or, the second one is just the opposite here. So basically, if you have 1 over b to the x power, b to the minus x power, sorry, then this is equivalent to just b to the x. So you can move that from denominator to numerator and flip the sign of the exponent. So these two rules here can pop up from time to time because of the calculations that we're going to be especially doing with certain examples. This is going to be one of the important rules to remember. Like I said, there are a lot of other rules that we can certainly take into account, but this is the one that probably is going to be usually the toughest of the bunch. So we want to go ahead and just just kind of showcase and say, hey, this is the most important rule. This is what we're going to run with. Okay, no problem. All right. So why is this important? Well, let's take a look at number 3, and let's see exactly what we're working with. Okay, next here says, how do we graph exponential functions, and what are some characteristics of the graph? Okay, so let's talk about exponential functions, and we're going to take a basic exponential function, and then we're going to be able to get some properties based off that exponential function. So let's go ahead and take a look at how we can suss that out. All right. Okay. So hello. All right. Boop, boop, boop. All right. So the function in question that we're going to take into account is going to be f of x is equal to 2 to the x power. All right. So f of x is equal to 2 to the x power. That's the one that we're going to go ahead and graph and get a little bit of info on. All right. So let's take a good look at this. So we're going to make an XY chart here, okay, for us to go ahead and plot along a graph here. Okay, now let's start off with the easiest number here. Let's go with 0. So if we plug in 0 in here, can anybody tell me what's 2 to the 0 power? What's that going to be? What is 2 to the 0 power? 0. Okay, so that's a 1. Okay. So we got two answers here, 0 and 1. Let's see what other people think. Is it 0 or is it 1? 2 to the 0 power. Is that 0 or is it 1? I'm going to agree it is one of those two answers. 1, okay. Let's see, anybody else? We got Planet, Anna, Jenna, Hannah. All right. So let's go ahead and take a look here. So the answer to this is going to be indeed 1. All right. So 1 is definitely our answer for this in this particular instance. Anything to the 0 power will automatically be 1. So just make a note here. Again, any note a to the 0 power is automatically equal to 1. So this is true for pretty much any number. Again, you could take a billion to the 0 power, and that's still going to be 1. All right. How about if we plug in 1? What do we get? What do we get if we plug in 1? Mm-hmm. 2? Okay, good. That's right. All right, let's try 2. What do we get when we plug in 2? All right, 4. That's correct. All right, so far so good. Okay, so we got 3 good points here. And we're going to pick 2 more points here, and then we'll put it on the graph. So let's pick -1. So if we choose -1, what do we get for y? What do we get for y? 2 to the -1 power. All right, so the answer indeed is 1/2. So remember, using our important rule to remember here, we have to change this from from the numerator to the denominator. So this will be 1 over 2 to the first. So this is going to be 1/2. That's correct. So this is a big reason why knowing that exponent rule is incredibly important. If we even try -2, again, 2 to the minus 2 here is going to be 1 over 2 squared. And so this is going to equal 1/4. Okay. Well, now that we have those values there, we can go ahead and put this all together here. So let's go ahead and do that right now. So let's put it on a graph. Ba-bam. All right, so we have 0, 1. There it is. 1, 2. Okay. All right. 2, 4. All right. -1, 1/2. I'll approximate here. Not an exact science with fractions. And -2, 1/4. So right about here-ish. Okay, so what does this graph look like? Well, if we put this together here, this is what the graph will look like here. This graph kind of goes up like that, and then kind of tails off down here like this. Okay, so this is the graph for 2 to the x power. Okay, and most exponential graphs are going to look something like this. So that's how most generic exponential graphs are going to look like once we put them together. Now, let's talk about some general properties based on what we see here in the graph of 2 to the x. So we can extrapolate a lot of different properties here just based on what we see. So let's talk about those right now. All right. Okay. So the first thing that we want to address here is that some general properties that you will see in exponential functions will be certain points. Okay, so certain points, this is for a general graph. Okay, so there's not much going on here. If we plug in 0, we got 1. So general properties, you get 0, 1. Some other points that are prominent here, of course, is going to be, say, 1, b, whatever the base of your exponent is. And as you saw there, again, -1, 1 over b. That was another prominent point that we have there. So that's where we got -1, 1/2. All right, so those are 3 prominent points that certainly occur on a generic exponential function. Okay, so that's the first property right there for the points. Okay. The next important point that I would like you to take a look at here is look at the graph here very carefully. This line right here that you see is never going to touch, it's never going to touch that 0. Essentially, it's never going to touch y is equal to 0. So in fact, for generic graphs anyway, we are going to have a horizontal asymptote. Okay, so we're going to have a horizontal asymptote here. So horizontal asymptote at y is equal to 0. So y is equal to 0 here is going to be our horizontal asymptote. So that's, again, another general property here of exponential functions. Okay. Now, right. A couple of other things here that we're going to talk about here. There's some in the book, but the ones I want to focus on are the ones that are probably going to be the most important. Yeah, we'll of course have to talk about that. All right. Next is talking about the domain and range. Okay, so the domain here let's discuss the domain. So the domain is pretty much everything. So you can plug in any number that you want in, and you're going to get an answer back out. So you're going to get, again, minus infinity to positive infinity. Okay, so that's the domain. All real numbers. All right, easy peasy lemon squeezy. However, due to having a horizontal asymptote here at y is equal to 0, we are going to get a different range here. And our range here specifically is going to be from 0 to infinity, but not including 0. So as you can see here on the graph, notice that we go from 0, but not including 0, we go all the way up to infinity. So that is the domain and range. Okay. And there is also one more property here that we're going to discuss here in just a second, but we're going to at least state it here for now. And that is, if you recall what we did back in chapter 2, we talked about transformation of functions. Okay, that's going to play a role here. So essentially, what I'm saying is that all transformation rules apply. So all transformation rules apply. So meaning shifting up, shifting down, left, right, okay, up, down, left, right, and reflecting on both axes, the x-axis and the y-axis, okay? So all those rules that we talked about way back in chapter 2, those things still apply to exponential functions that we see here, all right? No problem. All right. So are there any questions about that so far? We're going to look at another example, of course, but any questions so far? No? Okay. All right. Okay. Is the range always going to be 0 to infinity? Well, in generic graphs, yes, Hannah. The range is always 0 to infinity, but remember, that can easily change depending on what transformations occur depending on the function. So if you move it up, down, left, or right, well, those things that you see there on the general properties will also move around as well. So it's like saying if I move this graph down by 2 units, well, the horizontal asymptote is now going to change to y is equal to minus 2, and the range becomes minus 2 to infinity instead of 0 to infinity. So that's why I put that last one there, is that all transformation rules apply. So that way you understand it's like, okay, you can still move it around as is. You just at least have a starting point of knowing what the properties are once you have that going. Does that answer that question? I just want to be sure. Okay, cool. All right, so let's go ahead and do another example. Now that you have a good idea about what 2 to the x looks like, let's go ahead and graph another guy, and we're going to use 2 to the x as the backdrop here. So again, if you have this in your notes, keep in mind of this guy. So we're going to go do another one. All right, let's do this. So let's do 2 to the x minus 1 plus 2. Okay, 2 to the x minus 1 plus 2. So you notice that the x minus 1 here is indeed in the exponent. Okay, and we're just going to go ahead and see what we get here. All right, so before we start though, let's at least talk about the transformations that will occur that will certainly be shown when we actually do the graph. So let's go over it very quickly here. What does this minus 1 mean? What does this minus 1 mean in the function? Does that mean moving left, right, up, down? What does that reflect? What does that mean? All right, very good. So we're gonna essentially, we'll move right 1. Okay, good. Okay, and how about this plus 2? How about that plus 2? What's this plus 2 on the other side? Up 2. Okay, so we're going to move vertically up 2. Okay, good. So now we have an expectation. We know that transformation rules will apply. Let's go ahead and see how it bears fruit. So we're going to start with the XY chart here once again. So let's start off with 0. Okay, we usually start with 0 anyway. It's usually the easiest. How about 0 here? What do we get? What do we get if we plug in 0 for x? What do we get if we plug in 0 into this function? All right, so we get 2.5. Okay, we get 2.5. Wait, 2.5. Hmm. Uh, yes. Okay, that's correct. All right, good. So let's again. You get 2 times 0 minus 1. I had to think about that for a second myself. All right, so you get 2 to the minus 1 plus 2. So that's going to be a half plus 2, which is equal to 5 halves. Yes. Okay, good. All right, how about 1? What do we get with 1? All right, 1 we get 3. Good. 1 minus 1 is 0. 2 to 0 is 1. Plus 2 is 3. How about 2? How about 2? 2 we get 4. Excellent. That's right. And we could keep going, of course. 3 we would get 6, and so on and so forth. Minus 1 would be like 2 in a something, 2 and a quarter. So if we did this out here, so let's do this out here. Now, minus 1 is 9/4. Okay. So let's go ahead and put this on the graph here. So 0 comma 5 halves is 2.5. So 1, 2, 3. So it'll be right about here-ish. 1 comma 3, right about here-ish. 2 comma 4, right about here. And we'll go with negative 1 comma 9/4. So again, right about here. So you can see how this kind of pans out, and you see it follows exactly as we talked about before. Here's our exponential function, just like so, right? And we can see here again, we see in this case we have a horizontal asymptote here at a horizontal asymptote here at y is equal to 2, right? Because again, by the transformations, it did move up by 2 units, okay? Okay, any questions about that? Okay, good. Now, let's answer a couple more questions here regarding this graph. Can anybody tell me what would be the domain and the range for this graph? What's the domain and range for this graph? Let's start off with the domain. What's the domain for this graph? What is the domain for this graph? Okay, good. That's correct. Okay, so everything works. Negative infinity, positive infinity. Okay, now let's ask ourselves here, what is the range for this graph? What is the range for this graph? All right, 2 comma infinity. Very good. Don't forget we want a parenthesis next to the 2 here, right? Nice job, Ellerin. So there you go. 2 comma infinity here would be the range of this particular graph. Great. All right, so you can see how we get the range here. The horizontal asymptote really helps, and you can physically see that on the graph once you put 2 and 2 together. All right, great. Are there any questions about this example? No? No? Okay, great. Okay, now the next thing I want to talk about here is I want to talk about a very special number here in exponents that we're going to run into in this section and in the next section. So let's talk about that right now. Okay, so the next thing that we're going to talk about here in terms of exponents is we're going to talk about the very unique number e. All right, now e is a very special number here in mathematics. This is equal to 2.71828 1828 1828 1828 repeating. Okay, so this is a very unique number that stretches on forever and ever and ever. Now, this is used in a variety of applications here, as it is a very unique exponent. Now, in the book, there's a graph regarding E here, but what we're going to be using E here for, yeah, it's like pi. It's a transcendental number. That's correct. Pi is a transcendental number, so E is actually also a transcendental number. That's correct. It has its own unique properties like pi does. So what I want to kind of point out here is that what are we going to be doing with E here? Well, you can of course make graphs with E. There's an E, there should be an E button on your calculator here if you want to figure that out. Um, so on your calculator here, if you have the 84 here really quick, uh, like the 83 or 84, if you hit the second key on your calculator here and the ln key, which we'll talk about here today. So it's the second key and the ln key. That's going to be our friend. You'll get E and with a caret sign, or at least it'll be an E with a sign there. So E to some power is basically what you're looking at there in that instance. All right, so you could put E to the second power, and it'll give you some answer here, 7.389, whatever the case may be. No worries. All right. Now, the question is, well, where are we using e in this section here? Well, that's actually going to apply to our next couple of questions here. So let's talk about, our next question here. We'll talk about the formulas for compounding interest. So compounding interest is one of those kind of, hey, I can definitely use this formula for knowing how much I can put into my account and how much money will end up in my account after said period of time. So there are two types of compound interest. So let's talk about those. The first type of compound interest here that we'll discuss is going to be compounding over time. Okay, so this is like if you take a month, you compound, you take a month, you add a little more money, take a month, you add a little more money, you know, from interest, and you keep compounding over time. So the formula goes like this, and we'll describe what each of these letters mean. So, okay. All right, so here's our formula for compounding over time. It is equal to A equals P times the quantity 1 plus R over N to the NT power. Okay, so that's going to be our guy right there. Now let's describe what each of these letters mean so we at least know what the context is. All right, so A. So A here represents the ending amount. Okay, so this basically says, well, how much do you end up with after everything's said and done? P here is going to represent the principal. The principal is basically how much you borrow, the amount deposited or borrowed. All right. R is the interest rate. This interest rate should be in decimal. Okay. N here is the number of times you compound in a year. So for example here, if you see the word monthly, okay, then N equals 12. Okay, so if you see the word monthly, then you know that N is equal to 12, and then that's basically what you're going to work off of. All right, and then finally T has a very important purpose here as well. T here is time in years. So very important, time in years is always how that formula is going to go. Okay, so time in years. Okay, so that is compounding over time. I do have one more to state at the very least. Okay, now there is one more formula here that's compounding continuously. So this just basically means you're compounding in your account 24/7, 365. All right, every minute, every second of every minute of every hour of every day. All right, you are constantly compounding no matter what. So, how do we find what's the formula here for compounding continuously? Well, that's where our little friend e is going to come into play. So it is different than that of compounding over time. So A equals PE to the RT power, or A equals PERT, okay, like the shampoo. Okay, so A equals PERT. Good. All right, so these are the two formulas here. Again, P, R, and T have the same meaning as what you see above. Okay, there's no difference. P is principal, R is interest rate in decimal, and T is still time in years. Okay, so the meanings of the letters here, and A is still the ending amount. So the meaning of the letters here are the same exact meanings as what we have from before. There's no difference. Okay. So let's take a look here at an example. And we'll see how to do, say, compounding over time and compounding continuously. So let's take a gander here. All right. So suppose that you have $12,000 to invest. Okay. Which investment yields the greater return over 3 years? 7% compounded monthly, or 6.85% compounded continuously. Okay. All right. So here's our question. So we're going to suppose we have 12,000 bucks to invest. Which investment yields the greater return over 3 years? 7% compounded monthly or 6.85% compounded continuously. So let's go ahead and use both formulas here, and we're going to see which one is going to net us the higher result. All right. So let's look at the first one here, 7% compounded monthly. Okay, so that'll be this first part. Now let's go ahead and put in all the values here. So P here, again, is how much we invested. So we invested $12,000. All right. Really quick, what would R be equal to? What's R equal to here in our formula? What should that be based on this question? What should R equal to? That's correct, Elruin. That's right. So 0.07. So remember, 7%, but has to be expressed as a decimal at the end of the day. So very important there to go ahead and do. All right, nice. Okay, how about N? What should N be? What should N be equal to? Okay, that's right. N should equal 12, right? Because again, we're given here in this problem that we are compounded monthly, okay? So with compounded monthly, N has to equal 12. And how about our time t? What's our time t here? All right, our time t here is equal to 3 for 3 years. Okay, so far so good. Okay, let's go ahead and plug in the numbers then, because we have all the pieces, and we're going to use this formula, this first one you see here. So let's go ahead and do it, see what we get. So we get A is equal to P, which is 12,000, 1 plus, there it is, 0.07 divided by 12. And we're going to raise that specifically to the 12 times 3 power, just like so. Okay, now the next thing I want to talk about here is how to enter this in. One of the things about this formula here is there's a lot of parts in this formula, admittingly. So it's probably easier for you to go ahead and do it one piece at a time in the calculator here so you don't get it wrong. Plugging all this in at the same time on the calculator is really a big pain. So what I'm going to do first here is, instead of doing it all at once, I'm just going to take it in small pieces and I'll get the answer relatively quickly anyway. So I'm going to take 0.07, I'll divide that by 12, and I'll get some random decimal here. I get a 0.00583 repeating, whatever. I'm going to add that to 1 because, again, I'm just doing the stuff inside the parentheses here first. Then I'm going to take that answer, 1.00 blah, 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 58333. I'm going to raise that, and in parentheses, as you see there, I wrote that intentionally. I'm going to raise that to the 12 times 3 power or the 36th power. The reason why, sometimes you get larger numbers in there, so that's why I'm just kind of point that out. All right, in any case, so what you should have so far is something that looks like this. So let's see if I can at least show this on the calculator. Oh, this may be helpful there. So this is what it looks like on the calculator here. This is what I have so far. So hopefully you guys can see that. Okay. All right. So if I put that together, I'm going to have 1.23 da 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 da. And then I'm going to go ahead and multiply that by 12,000 after that. Then at this point, you should have your answer here of 14,795 and 11 cents. Okay, let me cut that, paste. Okay. No. Okay. All right. Are there any questions about that first part there? I'm going to get to the second part here, but did everybody get that answer on their calculator there? I just want to be sure. Yes? Okay. Again, I just want you to be sure that you can use the calculator appropriately here. So this is one of those, hey, let's get some calculator practice in. All right, good beans. All right. If you're having issues with the calculator, just let me know, then I can explain it again. Okay. All right, so let's talk about the next one here, which is compounding continuously. All right, so we're going to set it up using this second formula that we have here. We have all the numbers from before. We just have to go ahead and plug it in and see what we get. So we get 12,000 here for P, E, and then to the RT power, so again, 0.07 times 3. Okay, so this is what we have here in this case. Now, in this instance, you can enter it in all at once. So this one here is not too hard to do, entering it in on a calculator all at once. It should be pretty fast, straightforward. So again, you could go ahead and put 12,000 here. Now to find the E key once again, hit the second key on your 84 and hit the LN key. That'll bring up the E with the caret and the parenthesis. Or again, if you have the newer style calculator, it'll have E to that power there. And then you'll just put in 0.07 times 3. And we get here our final result for this. Yes, cursor, thank you. 14,804.14 cents. Okay, so if we compound continuously, this is what we're going to get here at the end of the day. And as we can see here, which one is our winner? It's going to be the compounding continuously one, just by a few dollars, not by a whole lot. So this is our winner. Right. Oh, did we not put the right rate down? What did we do? Did I put in, what was the rate? Was it 7? No? Let me check. Oh, you're correct. Oh, whoops. You are correct. I messed up there. That is perfectly fine, though. Let's make that adjustment, shall we? Thank you very much, Planet. I had made a mistake, but that's very normal for me. All right. So in this case here, that's correct. R here is going to equal 0.0685 instead of 0.07. So let's see what happens in that case. I think that's just as important. So let me do that again. Oh, okay, there we go. So 14,737.67 is what we get here. Okay. Okay, so in this case here, actually, the first one is the winner. So there you go. And it actually changes up our results here about which one's our winner, winner, chicken dinner. So, okay, good beans. All right. All right, and that is our final answer for that. Great. Are there any questions about that? Just make sure everybody's okay with that. Any questions? Okay. Nope. You're like, this is so easy. I don't have to try. And I'd be like, yeah, you don't have to try. Yeah, it's so simple. All right. Okay. Well, let's go ahead, and that is the end of section 4.1 for the most part. That's it. Good beans. Wasn't that easy? Wasn't that pretty fast? All right. Got that done in 50 minutes. All right. Bam. Easy sauce. All right. Let's go ahead and do the next section here, which is what number 5 and on is going to talk about here. So number 5, what does a logarithmic function look like? Okay, so now we're going to look at the exponent's counterpart here, which are logarithms. Oh, you just wait until I ask you my practice questions. That's fair. That's fair. That is fair. I said I would. You have that right. So what does a logarithmic function look like here? So a logarithmic function is going to look like this. We're going to have, say, y is equal to, and we're going to have, say, a log base b of x. So this is what a logarithmic function looks like here. It's either, again, y equals log base b of x, or f of x is equal to, again, log base b of x. Okay, so either one, you're going to see these quite often, of course, in some form or fashion. So there you go. Ew. All right. So the question is, well, that's what a logarithmic function looks like. So essentially, you could have, say, f of x equals log base, let's say log base 5 of 7. Okay, here's an example. You can put the numbers in there and be like, okay, let's just try and find that out. What log base of 7, actually, log base of 7x. Yeah, I guess I need an x in there. Maybe plus 2. You could have it look like this. This is fine. This is fine. This is actually a number, but yeah. Or you could have it look like this as well. You can have 3x minus 2 could look like this. Maybe these are in parentheses, for example. So maybe it looks something like this. That's fine. Whatever the case may be. That's okay. It is what it is. Now, what is important, though, is beside the definition, is actually looking at number 6, because number 6 is where we're going to get a lot of these properties and characteristics from, because what we want to do is we want to relate logarithmic functions to exponential functions. So that's what this next question talks about. So it says, what is the translation of a logarithmic function to an exponential function? So putting logs in a calculator is rather hard, unless you have a really nice robust calculator. So even on the 8384, you can't put all the logs in the calculator, like log base 5 of 7. You can't do that on a TI-8384. So how do we get around that, or how do we at least interpret it where we can sort of get around it? Well, here's how it's going to work. So we have y. So let's go with y equals log base b of x. Okay. All right. Okay. Translates to, so this is an equivalent. So it translates to, specifically, what does this translate to? Well, it's going to equal this, and so it's kind of important. So it says, now which way should I put that? Okay, I'll put it that way. All right, so b to the y is equal to x. Okay, so this is our translation that we are going to use here. So b to the y is equal to x. All right. Now, there's a very important note that I do want to make here in regards to this translation. Okay. One of the things that's important here is that sometimes we gotta ban people. Sometimes. All right. So sometimes we're gonna get confusing problems that may make it a little bit screwy, and I'll show you one of those problems here in just a second. But I want you to take this note into account. Note, okay, look at the positions of the letters. Okay, so look at the position of the letters. This is going to be very important, to look at the position of the letters, meaning to say, okay, the base for the log is the base of the exponent. Okay, the y here on the outside, or again, the letter here on the outside, is the exponent itself. And the thing you're taking the log of is going to equal that particular thing. Okay, the position here means more than the actual letters themselves. So let me show you what I'm talking about here in this case. Okay, so sometimes you'll encounter a problem like this, and this is, I want to get this problem here from the book. So yeah, so sometimes you'll see a problem. Sometimes a problem like this appears. So I'll show you what this looks like. Let's see here. Log base 6 of 216. So okay, let's say you have something that looks like this. X equals log base 6 of 216. I've seen this before, and it usually confuses a lot of people. So again, let me stress, look at the position of the letters and not the letters themselves. So if I were to translate this into an exponential, what would this look like? Can anybody tell me, what would this look like here if I were to translate this into an exponential? What would this translation be? Okay, that's correct. So in this case here, 6 is going to be the base of our exponent. The number here on the outside, whatever this is going to be our exponent. And that's going to equal the number we're taking the log of, 216. Okay, great. So if I wanted to solve for, in this case, x, 6 to what power is 216? What would that be equal to? 6 to what power is 216? Almost. Not quite. Almost, Gerda. You're just guessing. Don't guess. You don't want to guess in this class. That's pretty bad. We want to be firm and sure. That's why we set up the problems this way. Take away the guessing part. Okay, so x is equal to 3, okay, is what we get there for this problem. I can guarantee you guessing makes math like 10 times harder. It really does. Okay, let's try another one. Let's try this one. Okay, so how can we translate this into exponential form? Two to the ninth. All right, take a look at your letters here. Again, take a look at where these letters go. Again, take a look at the positions of these letters here. So be a little careful about this one. Okay, much better. That's correct. So again, this b here is going to be the base of your exponent. So that'll be 9. That's right. This 2 here will be your exponent. That's 2. And this is going to equal your x. And 9 squared is what? Hello! Hello, Skim. How are you? Annyeonghaseyo to you, sir. 81. You got it. All right. Nice work. All right. So far, so bueno. Okay. Let's do another one. Yes, sir. You're more than welcome to stick around, okay, Skim? Not a problem, my friend. Thank you, Skim. I really appreciate that. Thank you for the follow. Okay, let's try another here. Okay. All right, let's do that one. Okay. All right, so 5 to the 4th equals 625. Okay, so in this case here, we want to go backwards. I want to rewrite this in terms of a log. So let's take a look at 5 to the 4th equals 625. I'm going to go backwards here. I want to write it in terms of a log now. So what is this going to, how does this look like for a log in this case? What does this look like as a log? Again, you can write it as, I know chat's a little hard here, so for this, because it's kind of hard to write base b. So you could write it like this, log b, and then x like that. So if you want to write it like that, that's fine. I'll understand what you mean if you write it like that. Okay. That's correct. Okay. You guys got it. All right. Excellent. So 4 here would be our y. Again, our would be our what we wanted to equal. That's right. Log base, and in this case, log base 5 of 625. That is correct. Very nice. Okay. So far, so good. All right, let's do one more here. Let's do one more with this. Let's see. Yeah, that's fine. I can do that. Okay. All right, so this one's a little tricky, but how about the cube root of 8 is equal to 2? So the cube root of 8 is equal to 2. This one's a tad bit tricky, but it's not as bad as you think. Let's think of it this way, okay? So there's a way we can certainly think about this. So the best way to kind of think about this is rewriting. Oh, yes, that's correct. Very good. Oh, let me, yeah, okay, that's just fine. So let me go ahead and describe what this means here, what Radish kind of put down here. Another way to kind of express the cube root, and something that will come up in, let's say, a calculus class or whatever usually happens, occurs more often, but still, uh, why did I do that? Is this can be written as 8, and the cube root can be written as to the 1/3 power equals 2. So if you rewrite it just like that, okay, again, now you can see how you could put it together, because now you have a base, you have an exponent, you got an answer associated with that. So that's why here, in this instance, you have 1/3. 1/3 equals, again, log base 8, okay, of 2. All right, so that's where we get that answer from. So I know that one's a bit tricky on purpose. You know, that one's there to kind of challenge you just a little bit. But ooh, actually, I wanted to put the whole thing there. Why did I put it on? All right. All right. Any questions so far? Any questions? Okay. Now, the next thing that we're going to talk about here when it comes to logarithms is the properties, and there are plenty. So, this is going to be one of those things that, a couple properties of logarithms that we're going to certainly talk about here, that are definitely going to be applicable. So I'm going to leave a little room there. Okay, first and foremost here, for example, on your calculator, okay, you see the word log on your calculator, just straight up log, L-O-G. All right. However, log does have has a property associated with it. Log here on your calculator is indicative of log base 10. So if you just see log on your calculator, that's reflective of log base 10, a very specific base. So it doesn't include everything, it's a specific base here. The second property that we'll talk about here is also listed on your calculator here, and that is ln, or natural log. So ln stands for natural log. That's the key right below the log key on the 8384. And natural log also has its own unique base. This is going to be log base e. So that number that we talked about before in the last section is now making an appearance here in this section in determining what natural log is. Again, log base e is what natural log is equal to. So right off the bat, those are two things that we actually have to acknowledge here right away. Now, we're going to have a bank of a couple of other properties here. So these are some important properties that we use from time to time. So let's go ahead and so first of all, let's talk about general properties with logs. Okay. Okay, let's go over. Okay, so one of the first properties here of logs is log base b of 1. So if you take any log base b and you take it of 1, this is automatically equal to 0. Okay, anything to the 0 power is 1, and so this is our first property, like so. The next one here is if we take log base b of b. So if we take the same log base, if we take the base of the log and the actual number there happen to be exactly the same, well then this is going to equal 1. Okay? B of the first power is equal to b. Simple enough. Okay? Straightforward. Yes. All right. Next, we'll have log base b of b to the x power. So if we have log base b of b to the x power here, what happens here in this case is fairly simple. Essentially, you can imagine that the log base b and the b effectively cancel each other out. And that just leaves you with x, just like so. Finally, for this general one, b to the log base b of x. Let me try and get this as a... All right. B to the log base b of x. It's kind of awkward, but okay, we'll kind of run with it. B to the log base b of x is also going to equal to x, okay? So a b and log base b, once again, would cancel each other out the same way if you reversed positions. So a little weird, But yeah, that's how that one goes. All right. So those are some general properties there. Now, from the general properties here, we can also extend that out to, yes, I want you to stop. We can also extend that out to natural logarithms. So natural logs are going to work the same way, but because natural logs have log base e, here's how it's going to go. So natural log of 1 is 0. Pretty simple. Natural log of e is going to equal to 1. Okay, so natural log of e equals 1. This one here, natural log of e to the x is equal to x. And then finally, e to the natural log, e to the natural log of x, e to the natural log of x is also equal to x. So all these you can acquire from the same list as the general properties here. Okay. All right. Okay. Any questions about that? So those are some properties there for both regular logs and natural logs, which are just like, okay, no problem. So we can answer some of these questions now, some examples using these properties. So let's go ahead and do that. All right. So let's do some examples really quick. All right. So how about we'll go with all right, how about log base 4 of 4? What would log base 4 of 4 equal to? Log base 4 of 4? 1. Okay, good. That's right. How about log base 18 of 1? What's log base 18 of 1? 0. That's correct. Okay, so again, anytime you take log of base of whatever of 1, it'll always be 0. Let's look at another one here. 5 to the log base 5 of 77. 5 to the log base 5 of 77. What would that equal? All right, 77 is correct. All right, let's try another one here. This one here is a bit tricky, but that's okay. I think we're okay. Log base 64 of 8. Log base 64 of 8. Log base 64 of 8. Remember, this is 64 to some power, call it the x, equals 8, right? That's what this is equal to. 64 to some power is equal to 8. 64 to the first is equal to 8? 64 to what power is equal to 8? How are 64 and 8 related? Okay, good. That's correct. So remember that the square root is equal to 1/2. So one of those little tricksy things, okay? So remember that the square root is always the square root of whatever, a, is equal to, oops, put that there. Remember this is equal to a to the 1/2. Okay, so don't forget that little property there. That's fairly helpful. All right, one last one here. How about log base 7 of 7 to the 8th power. Log base 7 of 7 to the 8th power. What's that? Eight. Yep. Log base 7 and 7, they cancel each other out, and it leaves you with 8. Okay. Good stuff. Okay. All right. Good stuff. Okay. Any questions about that? Okay. All right. I know I have time, but well, we did answer question 9 here. So, what is a natural log? Natural log is log base e. So, you kind of answered that ahead of time. So, I'll just put that there. Okay. Now, I could get into characteristics of logarithms. Okay. Well. Okay, that's fine. Let's go ahead and do that. All right, we'll polish this one off here. Okay, so the next thing that we're going to do is talk about number 8. We'll answer this last question here, and then we'll be done. All right. So what are some characteristics of logarithms? So what we're going to do here is for us to gather some characteristics of logarithms, we're going to go ahead and make a graph here for logarithms. All right, much in the same vein as we did for exponential functions. Okay, so in this particular case, let's go ahead and pick an easy one here. So we'll pick here. Yep, that's always the simplest. Okay, let's go with something basic. So we'll go with f of x equals, or actually, forget f of x here. I want to change it up here. Y is equal to log base 2 of x. Okay, so we're going to go with y equals log base 2 of x. And we're going to go ahead and graph this particular function, and we're going to take a look at the similar characteristics as we did from the exponential one. But before we do that, well, we're going to need to go ahead and actually turn that into an exponential expression. So if we translated this over, what does this translate to? What does y equals log base 2 of x translate to? Okay, very nice, Planet. That's correct. Good job, Phantom. That's right also. All right, 2 to the y is equal to x. Okay, so this is going to be very important for us here. 2 to the y is equal to x is definitely going to be our guy here. All right. Okay, so let's make an xy chart here once again. Okay. So like we normally do, make an xy chart. Now, however, let's take a look at the answer you just put down. 2 to the y is equal to x. Well, if you look at this carefully here, notice that the answer here is dependent on what y is and not x. Now, normally we go ahead and plug in values in for x and we get stuff back out for y. That's what we normally do for pretty much every problem that we graph. But in this case, instead of going from left to right, this time we're going backwards from right to left. We're going to plug in values in for y and get an x value back out because of how we translated the logarithmic function. So we're going backwards here. So I'm going to start with 0 here for y, and we're going to get a value back out for x. Okay? So if I plug in 0 for y, what do we get here? All right, we get 1. So the point is not 0, comma 1, but the point is now 1, comma 0. Okay? And that's because it's easier for us to plug in a value for y and get x back out than vice versa. Now we could plug in other values here for y. We could plug in 1, and for x we get 2. Okay. We could plug in 2, and we get 4. And we could get, like, again, we could plug in minus 1, get a half. Try minus 2, you get a quarter. Okay, so again, just in this case here, it looks like a complete reverse of our original 2 to the x function that we talked about earlier. Now let's see what it looks like on a graph though, overall. So here we have 1, comma 0. We have 2, comma 1. 4, comma 2. Let's see here. We have 1/2, comma -1. So right about here-ish. And we have a quarter, comma -2, so right about here-ish. Okay, so let's take a good look here at our graph for the logarithmic function. So our graph's going to kind of look something like this. And this goes down like so, down here. Okay, so this is what a logarithmic graph is going to look like. In this case, log base 2 of x. Now, based on this particular graph, we're going to go ahead and pull out some properties or characteristics of logarithms. Yes. All right. So let's do that right now. Okay. First things first here, let's talk about points. Okay, so points. Points here, as you can see, as you may not be able to see, let me move that over just a smidge. There we go. Points here in this particular case for logarithms is going to revolve around 1, comma 0. Okay. B, comma 1. So the base, comma 1, that'd be the 2, comma 1 that you see over there. And 1 over B, comma -1. Okay. So those are some points there that are on the general. So again, just to reiterate here, these are general characteristics, okay, not specific ones. All right. Okay, next, after the points here, let's talk about some other things here. Next, as you can see here, we have in this case here, a vertical asymptote. So we don't have a horizontal asymptote, we actually have a vertical asymptote here. As you see, that graph starting getting closer and closer to x is equal to 0. So that's our vertical asymptote. Okay, so there's our vertical asymptote right there. All right. Next, let's talk about our domain and range. All right, now domain here is different. As you can see there on the graph, the domain now is going to be, in this case, 0 to infinity. So notice it doesn't cross 0 at any point in time. So our domain here specifically is going to be 0 comma infinity. However, our range here is going to be everything. So everything here is for the range. Essentially, if you want to think about it this way, probably the easiest way to think about it is everything's kind of reversed around from what we did for exponential functions. So kind of like mirror world in a way. So that's our domain and range for our functions. Now, let's take a good look here at the last part here, and that is, once again, just like exponential functions, since we could go ahead and change it to an exponential-like function, then that means that all transformation rules apply here as well. Okay, so all transformation rules apply as well, so just like they did for exponentials. Okay, so that's essentially what is happening there. And you just see, it would, again, it works out pretty much the same way. The only thing you have to be careful about is, of course, that you're going backwards from y to x and not necessarily forwards from x to y. So, okay, are there, yeah. Are there any questions about, logarithmic functions here? Nope. Okay. Okay. Nope. Okay. Now, the next thing I want to talk about here is, of course, this is pretty much the end of 4.2. So I'm going to stop there with the new material. Okay, at the very least, we may do an example from number 8 just to show off a graph of a logarithm. I know I don't really have a chance to do that here outside of this this one, but I'll show you how to do one next time because I want to kind of reserve this extra time here for you guys to ask questions from the review because I promised I said I would. And so that would be this time right here to ask questions from the practice test from Alex. So we'll go ahead and put that up here. I'll actually have to log in and get there, but I can do that. Okay. Okay. All right. Here we go. Okay. Here we go. Okay. So does anybody have any particular questions from the practice test that they would like me to go over, all right, today? Number 4? Okay, certainly we could do number 4. Okay, so let's answer the questions below about the quadratic function. Okay, Does the function have a minimum or maximum value? All right, well, let's go ahead and talk about that here first and foremost. Okay, so let me bring up the paint tool here for this one, and we'll go ahead and do it. Okay, so the first thing that we're going to do here in this problem is let's see if we can factor stuff out. Okay, if we can factor stuff out, we're pretty good to go. Well, if we could factor stuff out, that makes it easy to factor. But actually, well, wait a second. Oh, no, 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 not yet, not yet, actually. Now I gotta think about it. Let's not do that just yet. We'll do that in a second anyway. Okay, does this have a maximum or minimum value? Now, a here in this case is equal to -2. And that's actually really important here, Planet, because the thing is that if this is negative, if a is negative, so if a is negative, this opens down. And so because this opens down, the graph's going to look something like this. The graph flips over. It looks something like this. So what you do know is that you have a maximum here as a result. So for the first question here, the answer is a maximum because of the fact of what a is equal to there at the end of the day. Now let's talk about the last two questions here. Where does the minimum or maximum value occur? X equals to something. And what is the function's minimum or maximum value? Essentially what they're talking about here in these last two parts, they talk about finding the vertex. Okay, so if we find the vertex here, then we can answer the x coordinate for the second question and the y coordinate for the third question. Now, if you remember here, the way we want to do this here is we're going to use the shortcut here to find the vertex. Remember that our x value here for our vertex is -b over 2a. So I'm going to use this shortcut here in this case. So this is going to equal -16 all over 2 times -2. So here we get 16 divided by -4, and this equals -4. So the x value of the vertex here is going to be, in my case, is going to be -4. Okay. Now, as for the last part here, the last part suggests that to go ahead and say, all right, well, what's the minimum or maximum value? We're just going to take this -4 and we're just going to plug it into the original function. That's it. So to get our max value here, that's going to equal -2 times -4 squared minus 16. Again, this is f of -4. So, all right. Minus 16 times -4 minus 28. And so let's see what we get here. We get 16 times -2, okay, which is 32, this -32 here, plus 64 minus 28. Putting those together there, we get +4. All right, and that's going to be our answer for this problem. So it has a maximum value. It has a maximum value, and then it asks you specifically for the vertex of this particular problem for the next two parts. No problem. Any other questions from the review here that you'd like me to do? Like I said, if you have any other questions from the review, you could go ahead and ask. Number 5, okay. Well, that's this next one right here. So a supply company manufactures copy machines. All right. The unit cost C, the cost in dollars to make each copy machine, depends on the number of machines made. If X machines are made, then the unit cost is given by this. What is the minimum unit cost? So essentially, Planet, anytime you see the word like minimum or maximum, assume that, and you have a quadratic function here, assume that you're going to go ahead and find the vertex here, okay? Now, what it does ask us for is we have to find the minimum unit cost. So in this, in this particular case, we have to figure out what x is and then plug that in to the original function and then solve for y, and that's going to be our answer. So let's see what we get here for this particular problem. All right. All right, so this is going to be, again, A is equal to 0.8. B is minus 256. All right, C is 29,444. Okay, so we're going to do negative B over 2A here again for the X value of our vertex. So again, that's going to be negative 256 over 2 times 0.8. So if you do this on the calculator here, you get 256 divided by 2 times 0.8. So I get exactly 160. Remember to put this in parentheses here on the bottom together. Otherwise, if you divide and then multiply, it'll divide by 2 and then multiply by 0.8, and then you'll get the wrong answer. So be very careful about that, Planet, okay? Okay, now we're going to plug in 160 into our original function, and then we're going to get our minimum unit cost. So we have 0.8 times 160 squared, okay, minus 256 times 160 plus 29,444. All right. So we're going to plug this in here. Let's see what we get. 8 times 160 squared. Okay, minus 256 times 160. Okay, plus 29,444. Okay, so I get 8964 here as my answer. All right, and that's how I do that one. Any questions about that, Planet? Or any other questions for that matter? Any other questions from anyone else? No? Okay. All right. Are those all the questions you had for me, Planet? Or anybody else if they want to ask me any other questions? If not, then I guess we'll end off here. Oh, okay, you got another one. Let's go ahead and do that. 19, absolutely. All right. Okay, let's take a look here. The functions f and g are, okay, here we go. So these are the functions definitions, okay. For each function, find the domain, right? Each answer is interval. Okay, so let's look at f here first. Okay, so let's look at f first. So f here has x plus 3 over x squared plus x minus 6. All right. So if we have that there, all right, then we go ahead and factor the denominator here. So this is going to be x plus 3, x minus 2. And actually, I need to check one technicality about this problem. So let me look at something here. Okay, good. All right, just making sure about one little detail, but no, I'm okay. Okay, so here in this case, we get x minus 3, or x equals minus 3, I should say. And here we get x is also equal to positive 2. So x cannot equal these two values here. Okay, that's not possible. So we just, if you want to see what the number line looks like, all you got to do, again, just chop up that number line like we have from before. This is minus 3, this is 2, and just put parentheses everywhere since we can't divide by 0 here. So we're going to get our 3 intervals here. And in this case, it's going to be, let me go ahead and shrink this down. Move this across. So we're going to get here the first one, which is going to be negative infinity to negative 3. Then we'll union that with the next one at negative 3, comma 2. And then we'll union that with the last one here, 2, comma infinity. All right, so that's the answer for the first one. Now, as for the second one is actually even easier than the first. Now, we only look at the denominator here. We look at x squared plus 36. However, x squared plus 36 does not factor. Okay, it's not x minus 6, x plus 6. If that was x minus 6, x plus 6, okay, do understand why it's not the case, is because x minus 6, x plus 6 is x squared minus 36, not x squared plus 36. So because x squared plus 36 cannot factor, and we don't have an, and you could have it equal to 0, but still you have x squared equals minus 36. You take the square root of both sides, and you can't take the square root of negative 36. It doesn't apply here in this instance. So since we're talking about all real numbers here, well, that's your answer here, is everything. So negative infinity to positive infinity for that other one for G, and that's your final answer for that. Any more? Next one, okay. All right, graph all horizontal and vertical asymptotes of the rational function. Okay. So just have to be able to put all the vertical and horizontal asymptotes. Okay, so the first thing that we're going to do here is take care of our vertical asymptotes. So our vertical asymptotes is pretty simple here. Vertical asymptotes is we're going to set that denominator there equal to 0. So x here is going to equal negative 1/2 if we do the algebra out. So if we want to graph at least the first vertical asymptote, it has to be at negative 1/2. That's the first one. So let's go ahead and at least put in, I want this one. So we're going to put it right there. That's the first vertical asymptote right there. Okay. Now the horizontal asymptote is determined by the degree of both the numerator and the denominator function. So the degree of the numerator here is 1, and the degree of the denominator here is 1 as well. So if we want the horizontal asymptote here, we're going to take the coefficient, since this is degree 1, and this is degree 1. We're going to take the coefficient of the top, which is the leading coefficient, which is 6. Take the leading coefficient of the bottom, the denominator, which is 2. And then we're going to get 3. So our for horizontal asymptote is y is equal to 3. So we can put it right here. And there we go. We got it. Yeah. Those are the horizontal and vertical asymptotes of this rational function. That's it. That's all it asked us to do, so that's all I'm going to go with. Yep. Any questions about that? That's all you're doing for that one. Okay. Those are all your questions? Okay. Anybody else have any more questions that they would like me to answer? Fidel? Drivers? Whatever you guys want, so. You okay? You gonna tire me out? You're okay? Okay. Drivers, do you have any questions? All right, looks like he doesn't have any questions if he's not saying anything. All right. Okay, guys. I want to thank you guys very much for coming out to the stream once again. Thank you so much. You guys make it all worthwhile. You guys have yourself a very, very wonderful weekend. Okay, make sure you get that test done this weekend by Monday. All right. Otherwise, have a great weekend and take care of yourselves. Yes, we'll see you next week. Okay, everybody. Have a great one, everybody. All right. Take care of yourselves, everybody. All right. We'll see you later. All right.